Okay. Hey guys, I'm going to take you through Robert Milikan's oil drop experiment. His famous experiment is famous for two reasons. One, it's very ingenious, and two, it provided the first quantity or number associated with the charge of the electron. So it allowed us to determine the actual number to the charge of the electron. Before, all we knew was that the electron is negatively charged. This experiment allows us to say, yes, it's negatively charged, and here's how much negatively charged it is. Okay? So here's a very crude drawing of Milikan's oil drop experiment. This little perfume-looking like bottle right here actually contains just a bunch of oil. That's what's represented in this orange color right here. Okay? Now when you squirt this bottle, okay, and press on this little rubber tubing or whatever it is, okay, a whole bunch, just like in perfume, a whole spray comes out. Well, the same thing's true with this oil. Now these are very tiny oil droplets. Now, this top plate right here is positively charged. When he turns this on, he has a certain voltage applied to this power source. And this top plate is positively charged, and this plate right here is negatively charged. Now up here, it really doesn't have any effect on these, this being a positive. It doesn't have really any effect on the oil droplets, okay? Mainly because they have no charge. They're neutral, okay? Now, if an oil drop is going to fall through, it has this little hole right here. An oil drop will eventually just fall through here, and it'll keep doing what it's already doing. It's going to fall until it reaches that plate, right? However, what Milikan wants to do is he wants to suspend that oil drop in midair. He wants to just suspend it right there. In other words, he wants to balance out that force of gravity with some upward force. And in order to do that, first off, he's got to charge these plates. So it has a negatively charged plate down here. But the particle can't be neutral. It has to have a negative charge as well. Okay? And how he does that is he says, look, if I put a little X-ray emission something, whatever, some source of X-ray emissions, what it's going to do to the air in the chamber right here, which I haven't represented because I don't want to make it more confusing than it already is, what it does is it ionizes the air in the chamber. And you don't need to know exactly what that means, but basically what it means is it releases or gives up a bunch, if not all, the electrons in the air. So any electrons that are attached to the air particles, all of a sudden they're free from their electrons. And so you have a bunch of freely floating electrons just kind of floating around there, just up for grabs to anything that really wants it, if it comes through here. And so this oil drop is eventually going to come through, and as it's coming through, it's gaining and picking up these negative charged particles. Okay? And I'm going to represent that right here as this. So all of a sudden, let's just say it picks up 3 of those particles. Okay? So now the drop itself is negatively charged. And that's important because similar charges repel each other, right? And so if this is negatively charged right here, and the plate is negatively charged, and this is positively charged up here, so they're attracted already. If I have this at a certain voltage, which I can control right here, right? Sometimes if I have this at a low voltage, the drop might just slowly come down and eventually hit this plate. If I have this at a little higher voltage, it might very, very, very slowly come down, but eventually come down this plate. But if I have it at a voltage that's just right, maybe say here, right, it'll just sit there, right? If the electric force pushing upward is exactly equal to the gravitational force pulling the drop downward, then it'll just stay right there. Okay? And that can be represented over here. So here's a zoomed in box that would be like looking through this microscope. He puts his eyeball up to here, and he can see through here, and this is what he sees. Okay? Sees the droplets suspended there. Definitely doesn't see the electrons. They're way too small. Okay? And to model this droplet just sitting there, you got to know one main thing, and it's something that I already mentioned. The force of gravity has to be equal to the upward force, the electric force. Okay? Now, if the electric force is any bigger, the drop's going to go up. If the gravitational force is any bigger than the electric force, it's going to just fall down. But if they're perfectly balanced and the same size, the drop's just going to sit there. Okay? Now, this is important because you can write out an expression or an equation. You could say, well, the force of gravity is equal to the electric force. Now the force of gravity in other words, the weight of the oil drop is dependent upon two things. Okay, one of those things is the mass, and the other thing is the gravity of Earth. Okay, the gravitational strength of Earth. Now, we definitely know the gravitational strength of Earth, and Milikan also knows the mass of his oil drops. I won't get into how he determined the mass, but he knows it. Okay? As far as the electric force is concerned, that depends on two things as well. One of them is the charge of the drop itself, and then the other thing is, how much voltage did I apply? What is the electric field that is present in this scenario? So I'll just call it voltage applied. Okay. Now I know how much voltage I applied. Right? I could just look at my dial right here and say, oh, I applied 4.5 volts or whatever I'm measuring it in. So I know that. However, what I don't know, I do not know the charge of the drop. Right? I don't know the charge of the drop because in order to know the charge of the drop, I have to know the charge of at least a single electron, which is the whole point of this experiment. Right? I literally can't see the electrons. I don't know if this drop has 3 electrons or 1,000 electrons or 5 electrons or what, but even if I could, I don't know the charge of an individual electron, and so therefore I can't determine the charge of a single drop. Okay? However, because I know this entire equation right here is dependent upon these 4 things, I can set up an algebraic equation. I can say, well, the product of the object's mass times Earth's gravity is equal to the charge of the drop, which I'm just going to represent as Q, times the voltage applied, or the electric field applied, which I'm going to represent as E for the electric field. Well, if I want to know Q, all I have to do is just divide by E, the electric field applied, right? Because they're being multiplied. So when I do that, I get Q equals mass times gravity divided by E, the electric field applied. And so what this equation allows him to do is, he says, well, now I have a way of determining the charge of any drop of oil that I want. So what he does is he puts in some bigger ones, some smaller ones, some medium-sized ones, probably 1,000 different drops, right, and collects a whole mess of data, right? And this is where the key aha moment comes in. What he does is he has a whole mess of data about the charge of the drop, okay? So he says, well, one of my drops is, negative. This is going to be a very simplified way of it. Does not reflect literally the actual numbers that he got. But in order to get my point across, I'm going to simplify. He says, look, one of my drops has a charge of negative 1.6 times 10 to the negative 19 coulombs. Capital C is just it's an abbreviation in physics that stands for coulombs. That's a unit of measurement that's used to represent the charge of an electric field. Okay. He says the charge of another one of my drops is negative 3.2 times 10 to the negative 19th coulombs. Charge of another drop is negative 8 times 10 to the negative 19th coulombs. I'll do a couple more. Charge of another drop is negative 11.2 times 10 to the negative 19th coulombs. And then the charge of another drop is negative 16 times 10 to the negative 19th coulombs. Okay? So at first glance, you can't really see a pattern there, right? But if you look at it a little bit more closely, what you notice is, and what Milikan noticed, was that even though the charges of the drops are different numbers, in other words, 1.6 is a different number than negative 11.2, he notices something interesting, something that's very similar to how Dalton first noticed the idea of definite proportions and multiple proportions, that you can't have a half of an atom or 3/4 of an atom. If you're going to have atoms combining at all, it's got to be in these whole number ratios. Well, what he finds is, he says, well, if I take this number and divide it by this number, I realize that this number is twice as big. If I take this number divided by the smallest number, I realize that it's 5 times as big. Okay? If I take this number and I divide it by this number, I realize, oops, yeah, we're fine. I realize that it's 7 times bigger. Okay? And then finally, if I take this number right here, and divide it by this number, the smallest number, I realize that it's 10 times as big. Okay, what are the chances that it's just coincidentally these whole number ratios, right? That's too much of a coincidence. Nature has to be saying something fundamental about the charge of a single electron, okay? And so what he says is, oh, that means that if these are in whole number ratios, that means this number has 2 electrons. This drop right here must have 5 electrons. This drop right here must have 7 electrons. This drop right here must have 10 electrons. And therefore this one must have, just 1 electron. Okay? So what he just did fundamentally was he just discovered the charge of a single electron, which is negative 1.6 times 10 to the negative 19th coulombs. A very, 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 very small number. Okay? This number, 1.6, with 18 zeros in front of it. Now, today it's a little bit more precise, but still, early 1900s, very accurate, very precise way of figuring it out. So, anyways, I hope that helped. This will give you a foundational understanding before you come into class, or if you're gone or whatever, so that it's not completely foreign to you. So, I hope that helped.